First, let me say it's a pleasure and an honor here to be celebrating Dennis's 70th birthday. It's been many decades of wonderful mathematical and other interaction I've had with him. You might be thinking that I was smoking a controlled substance to change the topic at 10 o'clock at night, but I'm going to do it. I think I kind of represent the collateral damage. You know, in every operation, there's the operation itself, and then there's the accidental things that go on around it. And I'm representing this enormous sea of Dennis's influences outside direct subject matter where he's actually worked. This is really a truly tremendous thing that Dennis does all the time, bringing people together and just great. Anyway, here I am going to use some of the techniques and ideas I've heard from Dennis. I'm going to use them in a different place, and I use them kind of clunkily. I don't really control them well, and so I'm hoping that people who do control them well, who are experts, might become interested in what the subject's about. So the subject's about complexity. So let me first try to say what complexity is, because it's not at all clear to people. Complexity theory has to have a notion of a problem and a notion of the solution of the problem. And the problem has to have infinitely many instances. Otherwise, because you're thinking about how to solve this problem in the whole universe of potential algorithms. So if it's only one instance, the potential algorithm could have the solution to the problem built into it, and then there'd be nothing to do. So you need to have infinitely many instances of the problem in order even to have a subject matter. Then you need to have a notion of the size of the input of the problem, and you need to have a notion of cost of the computation to solve the problem. So that's the complexity theory. And you then talk about the cost of the solution in terms of the input size, and then you have the class P, the famous class P of problems that are solvable in polynomial time. So there are two examples I would want to give. One is 3-sat in a Boolean expression in 3-conjunctive normal form. You ask, is it satisfiable? This is the classical original NP-complete problem of Steve Cook, and it occurs in the context of it's X or Y or Z and W, or so there are three terms in the ors, and then there's a bunch of ands. And the other one is the Hilbert-Nullstellensatz, which I would state in this case is given a system of n quadratic equations and n complex, or perhaps real unknowns, does it have a solution? And the complex numbers are respectively in the real numbers. That's another example of a problem. And these two problems are both NP-complete problems in the different contexts in which we discussed them. The first one is in the context of Turing machines, and it's the 3-sat problem is Cook's famous first NP-complete problem, and it's the origin of the question is P equal NP. And the second one is the Hilbert-Nullstellensatz is considered for these machines sometimes called BSS machines, in which you can actually think of them as kind of a Turing machine, but you can actually put a complex number instead of a 0 or 1 in an element of the tape, or a real number, or perhaps an element of some ring.
What does NP-complete mean?
It means if this problem is in P, then all other problems that are in NP are also in P. So one of our goals back in 1989 when we started this theory was that we wanted to build a theory of complexity which addresses the problems of numerical analysis and scientific computing. So here, I really didn't do that. I'm giving you problems, and I'm saying you put a complex number, an actual complex number in the tape, and then you can multiply to or add to, and you get the actual answer. This is not a realistic model for a computing machine. This is a very clean a very clean model, and the problems that emerge are very clear. We have, for example, the class P, the class NP, NP complete problems, all such things. It's a very clean theory there. But here, whoops, what did I do? Here, when we want to talk about numerical analysis, it's a completely different ballgame. And I must say that we said this in 1989, and we haven't done it. It's still very much a work in progress. It's very difficult to pin down the good concepts of what you have to take into account. For example, the sensitivity of the answer to the problem instance, or questions like that, stability, error analysis, error in the input. All these things have to be taken into account, and we haven't really done it.
You indicated that a complex number has infinite amount of information, so somehow that's an issue, but it's not clear to me whether you're assuming the issue in the first example and not in the second, or vice versa.
Exactly. This here,
explain that.
here I'm assuming you've got the complex numbers as a field, and you do field operations as you would.
You're allowed to multiply two numbers.
Like when you open Alford's book, it's the same as Alford's book. You're allowed to multiply two complex numbers.
That's not very realistic.
Well, I don't know what realistic means. We can discuss how the models, what models might be.
Well, you're saying with that assumption, these two
things are very clear.
Complex numbers, but the second one does.
The second one allows you to use complex numbers. First one, you only use zeros or ones.
Right.
Second one, you allow yourself to use complex numbers. You get a theory.
So
We may discuss whether or not that theory means anything for the real world. I would say it's
allowed to multiply, that's one cost of one.
cost of one, yeah.
Okay.
Cost of one, exactly. And you get the exact answer. And you can check for zero. You can say, is this number zero? You check for zero.
And on the next slide,
The next slide, I'm thinking about problems where there may be, the input itself may not be exact, and the computations may not be exact. So I'm thinking about that now, and it's much harder to make a very clean theory here. What do you count as cost?
here you're trying to get rid of this unrealistic assumption that a cost one for doing arithmetic operations. You want to do it with
Yes.
approximation. Okay.
If I can get a clean theory that says something about reality, in all cases, yeah?
Can I make a comment? You know, if you look at phase transitions, in order to...
I only have a half an hour, you know.
Yeah,
And there's a bus coming, so please...
If you look at the phase transition, in order to capture the phenomenon, you are obliged to go to the limit of thermodynamic limit, which is not in physics. And there you do the theory. And you describe what you see with a infinite volume. So it might have the same effect here. I mean,
it might, yeah.
The model does not need to be realistic to be able to describe reality.
In the end, the question is how well it defines reality. So, but we haven't gotten a good model here altogether, I'd say, in the numerical analysis world. The model problem is solving polynomial systems of equations. So here I'm going to try to quickly introduce the spaces and objects of study. So I have n homogeneous polynomial equations of degrees d1 through dn. I consider the vector space of such systems with the fixed degrees and the number of variables x0 through xn, and they're supposed to be homogeneous. Then I have what I call the solution variety, which are the pairs f zeta, such that f of zeta is 0. And inside the solution variety, I have the subvariety of places with simple roots, f comma zeta, where zeta is the simple root of f. And attached to a simple root, I have a quantity which I call the condition number. This condition number is essentially the, let me see if I do this. Oh, look at that. No. It's essentially the inverse of the derivative at the root. And then you have some normalizing factors about, since it's in projective space, you have to worry about scaling and making it homogeneous with degree 0, and there's something to do with the degrees here. So this is essentially the inverse of the derivative normalized to make sense in the projective space. Okay, so now you want to solve a system, and the method we're going to study here to solve the system is to pick a system and a solution you know, to pick a path between the two systems, the system you know and the system you want to solve, and try to continue the solution along the path. Okay, so that's the methodology that we're mostly going to be considering, and the way we're going to numerically follow this path is by applying Newton's method and incrementing the parameter. So we start with t0, we know the solution, then we get a little delta, t0 plus delta, use Newton's method, and the approximation to the root at ti to approximate the root at ti plus 1. And finally, we output the last value, and that's the approximation of the root of f1. So the question is, what's j in this system? Okay. If you're going to actually guarantee that this actually works, you have to actually give an algorithm that does this and tell you how to increment the t and estimate the j at the end in terms to know the complexity of the algorithm. So Steve Smale and I worked on this problem in the 90s a lot, and we didn't solve it. We didn't find a really good uniform algorithm to solve this problem in polynomial time. Now, I'm talking about one root. I'm looking for one root of a system of equations which may have exponentially many roots, right? I may have a system of quadratic equations. An n variable should have 2 to the n roots. I'm only trying to find one of them. And I want it to be polynomial in the input size. The input size, in this case, is the number of coefficients. Quadratic equations have n coefficients, and there are n equations, more or less. I have n squared coefficients, more or less. There are n equations, so I have more or less little n cubed input size. So I got to tell you, I might have 2 to the n roots. I'm asking you to find one of them. So we didn't quite solve the problem, but recently there's been actually a huge amount of progress by Beltran and Pardo and Burgieser and Kuker, and these homotopy methods play a big role in their solution of the problem. So here's the first step that's done. What is the number of steps that you need to follow this path by Newton's method? So the path is f of t zeta of t, and at each point I have a condition number. If I look at this integral, if I didn't have the mu there, this would be the length of the path in the variety w. But now I've multiplied this normal Hermitian structure by a conformal number called the condition number at the point. So I've changed the metric. And I'm saying that the number of steps is the length of this path in that metric. It's at most that. The number of steps is at most the length of this path. It's probably at least at 2, actually. It's sufficient, I should have said, I'm sorry. Number of steps sufficient. Right. I'm sorry. Yeah. Good, thank you. Number of steps sufficient. Oh, it's bounded by. Well, sufficient is bounds necessary. So, anyway, that's this number of steps will do.
Sufficient is bounded above 5.
Mm-hmm.
The number of steps sufficient is bounded above 5.
Yes.
Well, what you mean is that number will do.
That number will do. And I'm going to take that number in my complexity estimates, to do my complexity estimate. Okay, so now I have to give you a specific algorithm. So I'm going to give you one starting point, f0 zeta 0, and I give you an f1. And the simplest thing in order to have a specific algorithm is just to take the straight line between f0 and f1 and try to continue along that straight line. And then you can talk about the average cost of doing that, and you would then integrate this function over the set of all possible f1s and take the expectation of this integral. And that's a number that now estimates the average cost of finding one root of almost all systems f1 starting from f0 with the root zeta 0. So we say if it's a good starting point, it's a good starting point if that number is small. So the first theorem of Beltran-Pardo is that if you can pick the root at random, it is the expectation of that function is small. It's very polynomial. So from a probabilistic point of view, and they tell you how to construct a random system and a random root. So you can pick a random system, random root, and then if you do that and you try to solve all systems with that system root, you look at that, how that varies over the space of all possible choices. The expectation is small, which means that if you pick 1, 2, you'll be doing fine with a couple of choices. So that's really a super result. Burgieser and Kucher actually give a deterministic algorithm to do this. They give a starting point and a starting system and a definite point. And they produce also if the degrees of the system stay bounded, like our case, 2. For quadratic systems, they produce a deterministic polynomial time algorithm, which on the average is polynomial time cost and produces an approximate 0 with probability 1 of every system of equations. So that's kind of striking, I say, because the problem I showed you in the first chart is this problem of does there exist a solution in affine space is NP complete. And here you find the solution in polynomial time, sort of approximately. So it's really kind of a striking opposition of things that are happening. You actually find the answer in polynomial time, you can't decide, and you don't think you can decide if there is one in polynomial time. Okay. So there were 3 ways now to find these starting points. One is Beltran-Pardo, pick one at random. Another one was to take the most simple system. This is the best condition system. It has the smallest condition number of all possible systems. It is the furthest away from the discriminant locus, which is the locus of points f zeta where the rank is deficient. It's the furthest away. So if I were thinking back to my old, almost just postgraduate days at Berkeley, I would think there would be Thurston, and he'd say, you're looking at it, and you get furthest away, it looks smallest. So that's the best place to start, where it's furthest away, and so the bad spot looks smallest. Well, that's just a conjecture. It's not been proven. The third one is the one that Burgieser and Kucher use, which is essentially the d roots of unity. So let me go back to this function ag e naught being small and just say a word about it. There was that function g that I just had that we thought was the good system. This function, I would conjecture, is a equivariant Morse function. It's equivariant for the action unitary group. This function is conjecturally an equivariant Morse function with only a critical orbit of minima, one critical orbit of minima, no other critical points, and the critical orbit of minima is the orbit of the good starting point that Smale and I conjectured. So that would solve everything, but that's, for the moment, just a conjecture. So if we go back, though, oops, I'm going the wrong way, huh? So we're really up to here. These are the good ones. But how well could you do? So then that's the question. Maybe you can do better than straight lines. And what the best you can do, according to this method of analysis, is to take geodesics in this new metric, right? Those give you the shortest paths. And if you could find these geodesics, what we prove here is that the Beltran-Pardo estimate, which was little n, capital N is the capital N is the dimension of the space, little n is the number of variables, would actually be replaced by the log of capital N. So it would be a huge, huge improvement if you could find these geodesics. And that would seem to say also that if you can sort of understand their properties, you could maybe design algorithms that wouldn't exactly find the geodesic, but would somehow mimic their properties and be much, much more efficient. So the question is, what are these geodesics like in the new condition metric? So let me warn you now that this new Riemann structure, it was the norm of the inverse of the derivative. So the norm is not a smooth function. The norm is a Lipschitz function. It's like the absolute value. It has directional derivatives everywhere which are continuous, but it's not a differentiable function.
To the discriminant locus.
Yeah. Well, it is comparable.
To 1 over the distance.
To 1 over the distance, yeah. It's comparable to 1 over
Like
the
that.
Hmm?
You
So
like
that-
that metric.
I like that metric. Yeah, I like that metric. So that's the fact. So that's what I started. So I said, oh, it's comparable to 1 over the distance. What do I know? I've been sitting in Dennis's seminar every day, every Wednesday. And he comes in every Wednesday and he draws a straight line and there's an upper half plane and there's these circles. And so it's 1 over the distance. So what are the properties of something we multiply by 1 over the distance? Well, the properties are, for the geodesics in the upper half plane, is that the geodesics move away from the x-axis. And in fact, if you think about it a little more, the closest they get is at the endpoints. And then you can say, oh, okay, if the closest you get at the endpoints, that's like convexity. Right? So this function, 1 over y, is supposed to be convex on the geodesics that are defined by changing the metric by 1 over y. And in fact, if you even take the logarithm's convex. So all powers of 1 over y are convex on the geodesic. So I had to think, well, maybe that's the same for these metrics. Oh, I only have 5 minutes. Okay, so that's the question. What can we say? It's true in the linear group. It's true in the linear solution variety. I don't know if it's true in the nonlinear solution variety. That's the situation we're at right now, and I'd love to know if it's true in this variety V. When all the equations are linear, then this is a proven theorem. So you might ask the question, in general, suppose you take a smooth Riemannian structure and you multiply it by a function, and then you ask, when is this function log convex on the geodesics in the new metric that it's defined? So then you could give if the function is differentiable, you can give a differential condition. It says if this is satisfied, then it is log convex. But an example of that would be if you take a submanifold of Rn and you use 1 over the distance. So you change 1 over the distance, but now it's smooth, but it's not smooth everywhere, because when you get to the points on, like if you take the manifold to be the x-axis union the y-axis, then 1 over the distance is this distance here and this distance. The minimum is this distance here and this distance here. The function's smooth here, but it's only Lipschitz over here. So you have, I don't care, I'm just telling you. So, oh no, because you can't use this condition. So now what do you say about, how do you characterize, how do you know when the geodesics are, when you have convexity? So, and what are the geodesics like? So when you have Lipschitz, so here yes, but here, you see you might come like this, run along here, and then come off. You might come off on the bottom. So here you see right away, no uniqueness of initial conditions. The situation is a little bit different. But it turns out that we can say the following, that the geodesics are C1 with Lipschitz derivative, that the initial value probably not have unique solutions, that there may not be locally unique answers just for Lipschitz things. Just take 2 flat disks, put them together like you might with a, what do you call them, a pouch or what do you call them? Thimble, a thimble. Then you have these 2 geodesics, one on the top face and one on the bottom face. So there's no unique geodesic locally necessarily for Lipschitz system, but I'd like to know if it's true here. But then there is a theorem. So if you can decompose the space, as it turns out we can in the linear group, into the different orbits of the unitary group, and on each one of these orbits we can see that we do have something C2, and we can prove convexity on each one of the orbits, then we can piece them together. So the geodesic, we don't know how it crosses here, but it may, for example, I don't know, not in this example, but it may somehow wiggle across. So how do you deal with that case? And when it's dealing with that case is you try to compare the geodesic in the ambient space to the geodesic in the subspace. And now it turns out if you do, F equals ma, so that's really x double dot equals the gradient of some function. If you restrict that to a submanifold, you're restricting the gradient. Restricting the gradient is to project it into the submanifold. So the projection defines the geodesics up to second order in the submanifold. So this case, it's not at all obvious. Right? These two curves parameterized. You parameterize this curve by arc length, this curve by arc length. You project this in by the normal direction. The two curves are tangent to second order here. It's not even obvious for the circle, but it's true in Riemannian manifolds, and it's even true in this situation where you've got only Lipschitz functions, and where the only way I can see to do it is you look at the second order divided differences. You see if it's not convex, then it has to be negative on a set of positive measures. Then you have to take a density point. Then you have to do this usual structure. You have to apply this piece of geometry and then conclude that it couldn't have been convex in the submanifold. So you can piece together the pieces, and that's what lets us do it for the general linear group, where we can also exploit the orthogonal or unitary groups to reduce the problem to diagonal matrices, more or less. The symmetries are something I don't understand in that case, because I think there are much deeper connections to a lot of things here, because the norm of the inverse of the matrix, in the case when you have the unitary group operating on a space of general linear group, is given to you by the moment map. And you take the moment map and you look at the Weyl chamber, and you see where the orbit intersects the Weyl chamber. You look at the smallest eigenvalue in the Weyl chamber. That's the norm of the inverse. So there's somehow a connection with much more geometry going on here that I'm not understanding. But I was hoping that people could get involved and see how these things affect complexity. I have a feeling that you can't avoid the condition number as a complexity invariant when you don't have precise data, or you're just looking for approximate zeros, and then you have to deal with it somehow. Anyway, that's the geometry. Thank you, and I hope the bus hasn't left.
Araceli reports that the bus hasn't left and is waiting patiently, so we have time for a few questions.
Well, why did you want to know convexity?
I just started thinking, what are the properties of the geodesic? So, in fact, you see here, so it's different.
Can you say what the statement was? What's convex? What's supposed to be convex?
The log of the condition number on the restricted to the geodesics in the condition number. And that would say you should not be moving close to the discriminant locus. You never get closer than the endpoint. You stay away, and if you're starting to get close, you know, on the straight line, you know you're in a bad situation. So you may then want to do something to, where's the chalk? They want to do something to alter what you're doing. And so what is, for example, if you have one point as your manifold in R2 or in C, and it's 1 over the distance to the point, what are the geodesics? Well, the circles all have the same length because it's 2 pi r, right? But then it's times 1 over r, so they're all 2 pi. So all the circles have length 2 pi. So if you were coming along and suddenly you see your condition numbers getting big, you want to pick up a geodesic and go around and come out the other side. So that clearly should change sort of the one variable picture. And in the n variable situation, you might have you know, some sort of cusp, and this is the S1 singularities in the discriminant variety. And then if you're coming in the discriminant, the condition number is getting big, you should go around here and come out those. Which means you solve another problem. When you get here, the condition number is big, you find a point on the discriminant locus, and you use it to pivot around. So some algorithms in one variable actually work that way. When they're getting in trouble, they look for a 0 of the higher derivative as an organizing point for clusters or things like that. So this would be a way of trying to exploit some of the geometric information that's easy to get near the highest codimension strata.
In that example, you should go around the circle starting at the beginning point.
Yeah, I know, but it's not.
Suppose you don't know. I see
You don't know. Yeah. You don't know you're in trouble.
You don't know you're in trouble.
All right, and you
You're
don't know.
already in trouble. Okay.
Yeah. Yeah. So anyway.
That's the way you choose the circles that you choose.
This one here, no, I don't know. I've not devised an algorithm here, so I haven't thought about this seriously. I keep trying to prove these other things I'm talking about. So I haven't thought of actually analyzing this algorithm. I'm sure it would work should work much faster. But it's another question. It's another big project. Here you see there are other roots. So I mean, in the polynomial, it's not exactly like there's a root here too.
So what's the geometry of the set you want when you have more variables? It's like a bunch of like the x-y axis there. Is that typical?
It's like the determinant variety or the singularity.
You have lots of different equations. So
No, it's like singularity theory. It's maps.
oh, it's a map from n variables to n variables.
Basically,
so it's the determinant variety of that non-linear map.
Right.
Oh,
So it has a not terrible complexity to it, but a determinant variety has a universal singularity. So you can get as bad as you want, but the codimension goes up very high. So from a practical point of view, you're not going to encounter the higher order singularities very much. And so this type of algorithm could work on the average very, very well. I didn't tell you what average I was taking. The average is with respect I put on the space of polynomial systems, the L2 in a product. Normalized so that the norm of Z0 to the D is 1. So I just take L2 normalized like that, and then that's the Hermitian structure I define in HD, and then it's the probability with respect to the Fubini-Study metric on the projective space.
Questions for Mike? Okay, let's thank him again and go catch the bus.